Hello. I'd like to begin class today by giving you a warm-up question. We have it pictured here. A rock is launched at different angles with the same initial speed. Which angle will provide the longest time in the air? So we're talking about the longest time in the air. Are we talking about A, B, C, or D? I'd like you to go ahead and have a conversation with your partner. When you think you've come up with an answer, go ahead and resume the video. For now, pause the recording so that you have that conversation with your partner. Okay, so hopefully you've come up with a prediction. Remembering what we've studied about projectile motion so far, we have looked at projectiles that basically have been half of a parabola, and we have learned that the height is what determines how long something is in the air. And as a result, in looking at this problem, we're looking at which of these is going to provide the greatest height. And as a result, if you make the connection between height, vertical height, and time in the air, you'll see that D is in fact the answer that would result in the projectile being in the air the longest. All right, so what we're going to do today, we want to spend some time looking at the other half of the parabola. For instance, like I mentioned, we have been spending most of our time with projectile motion launched horizontally. But like we did in the lab before, we actually have the entire arc in projectile motion. So that's what we're going to look at today. We're going to look at solving a problem that actually travels in the full arc, like we've seen in our video in the paradigm or the opening lab. So for this problem, we want to solve for three things. We want to figure out how much time it's in the air. Hang time is time up and time down. We want to find out the height that it reaches, and we want to find the range. And this is how far it goes in the horizontal direction, while this is how far it goes in the vertical direction. So here's the information you're given. We're going to be told that our launch velocity is just 20 meters each second, and we have an angle of 50 degrees above the horizontal. So what do we do first? Well, remembering our model for projectile motion, it says we can treat projectile motion as two independent motions happening at the same time. That would be a horizontal motion, that is constant velocity, and a vertical motion, that is accelerated motion because of the force of gravity. So let's take our understanding of trig and let's figure out what these horizontal and vertical components would be. So in the vertical direction, the y component is going to equal v0 times, and this is 50 degrees, times the sine of 50 degrees. So that's going to be 20 meters each second times the sine of 50. Make sure you are in degree mode. And we get our y component to be 15.32 meters each second. And this is v0 in the y direction. We'll do the same thing in the x direction. I'm not going to call it v0x though. Does anybody know why? Well, if you remember, in the horizontal direction, the velocity is constant. So we can just label it as vx. We'll take that 20 meters each second, multiply it by the cosine of 50, and we get 12.86 meters each second for Vx. So now that we have identified those two velocities, we're not going to really use the 20 meters each second anymore. We're going to now focus our motion on this two different components, the horizontal and the vertical. So let's begin with thinking about the horizontal. What do we know about the horizontal motion? Well, all we know really right now is that Vx equals 12.86 meters each second. We don't know how long it's in the air, and we don't know how far it goes. So it looks like we need to maybe look over at the vertical motion and see what we can explore from this. Now, if we think about the motion of a projectile, we know that at the peak right there, the vertical velocity is 0. The vertical velocity is 0 at the peak. of this motion. That is going to be critical for us to have some information. We know the initial velocity in the y direction is our 15.32 meters each second. And we know our acceleration is negative 9.8 meters each second squared. Let's find the time to the peak. That will be something we can solve for. So from this given, we can go ahead and use our formula VF equals A delta T plus V0. And these are in the y direction. So I'm going to go ahead and when I plug in that the final velocity is 0, our acceleration is negative 9.8 meters each second squared, our delta T is our unknown, and our initial velocity was 15.32 meters each second. When we do this, we get a delta T of 3.12 seconds up and down. What you'll notice is if you actually solve for delta T, you actually get delta T to equal 1.56 seconds in this equation. That is to the peak. All right, now that's a really big piece of information because now that we know the time that it's up and down, we can go back to the horizontal direction and use this delta T of 3.12 seconds with our horizontal velocity equation. Delta X equals Vx times delta T. We multiply our 12.86 seconds, or 12.8 meters each second, times our 3.12 seconds, and we get a range of 40.12 meters. So that is delta X. We've solved for the hang time. We've solved for delta X. With those pieces of information and what we've solved for, we can go ahead and solve for the height, which would be the last piece. And by solving for the height, you want to think about, are you going to use the hang time up and down or just the time to the peak? I would recommend using just the time to the peak with one of your kinematics equations. You'll solve for a delta y and get about 11.97 seconds. So this is one example of solving a projectile problem that is launched at an angle and is landing at the same height at which it is launched. I'm going to give you a chance to work on a couple practice problems like this. At this time, you may work with your neighbors to solve them. And if you have any questions, see if you can resolve them by using the solutions that are up in the front of the room as well. Good luck, and I hope it works smoothly for you.